Okay, so now we have to talk about the math problems that relate to the heating and cooling curve. Now we went over the different terms, specific heat, heat of fusion, and heat of vaporization. But understanding them and understanding where they lie on this chart will make sure you'll never have a problem. And I'll show you what I mean. Let's talk about heat of fusion first. And now you're dealing with a math problem, and you're like, oh no, I have to memorize another formula? No. You go to reference table T, and it's right there. It says heat calculations. It's right there. Now, there's a lot of different things that it says there, but we're talking about heat of fusion, so let's talk about that. The formula is Q equals MHF. And it says on table T what Q equals, what M equals, and what HF equals. Q is the energy, M is the mass, and HF is the heat of fusion. Now remember, heat of fusion is the amount of heat required to change just 1 gram of a substance from a solid to a liquid. And it could also be used from a liquid to a solid because it's the same thing. Because remember, on here, you're dealing with solids and liquids, the phase change. So it doesn't matter if you're going from here to here or here to here. It's still the same heat of fusion. So the formula is Q equals M HF. Now you're probably thinking, oh no, heat of fusion, I don't know the heat of fusion. I don't remember how to do that. Well, you don't have to remember anything. You go to table B, where it lists the heat of fusion for water. Table B, as you can see in the slide screen, shows the heat of fusion for water as 333.6 joules per gram. So you have it there. So the formula is Q equals M mass times HF. So what if they gave you a problem that said, calculate the heat released when 25 grams of water freezes at 0 degrees Celsius? Well, freezes is not fusion. Freezes is liquid to solid. But it doesn't matter because it's right on here. Where is freezing? Freezing is line segment BC right here. And if you're dealing with that, then you're dealing with the heat of fusion problem because that's what is happening at BC. So the formula is Q equals MHF, heat, Q is heat or energy, equals mass. Okay, what's the mass here? Well, we said 25 grams of water. So the mass is 25. What's the heat of fusion of water? Well, we said on table B, it's 333.6. Therefore, the formula is Q equals 25 times 333.6. And when you put in your calculator, you get 8,340 joules. So in this case, it's very simple. If you know you're dealing with this area on the heating curve, you know you're dealing with Q equals MHF. And they could say freezes at 0 degrees, melts at 0 degrees. They could say changes from solid to liquid, changes from liquid to solid at 0 degrees. But if they're talking about water, they give you the heat of fusion on table B. If they're not talking about water, they could still do it, but they'd have to give you the heat of fusion, and then it would be even easier. So in this case, you're dealing with heat of fusion, you're dealing with line segment BC, and you're done. Q equals MHF, mass times the heat of fusion. It's a simple math problem. Heat of vaporization is also simple. Where would heat of vaporization be? Well, remember, heat of vaporization is the amount of heat required to change 1 gram of a substance from a liquid to a gas, vaporization, which is right here. So remember, the same amount of heat going from liquid to gas is equal to the amount of heat going from gas to liquid. So it's exactly the same. But you know you're dealing with heat of vaporization. Well, let's see. What's the heat of vaporization of water? Oh, God, you don't remember? Who cares? Go to table B. It's right there. Heat of vaporization of water, 2,260 joules per gram. They can't make it any easier. And table T has the formula. Q equals MHV. It's that simple. So what if they said, for heat of vaporization, how much heat is needed to vaporize 25 grams of water at 100 degrees Celsius? Now, why are they giving you 100 degrees Celsius? Because that's the boiling point. That's where it's going to be vaporized. But remember, it's still Q equals MHV. Heat equals mass, 25, times the heat of vaporization, which is different than the heat of fusion. So you go to table B, you see it's 2260. Q equals 25 times 2260, and you get 56,500 joules when you plug it on your calculator. And it's that simple. And again, they could say vaporize at 100 degrees. They could say go from liquid to gas, go from gas to liquid, condense. Anytime you're dealing with this part of the heating curve, you're dealing with heat of vaporization. That's it. And one of the things you should notice, though, is notice that the amount of heat required to vaporize something is more than the amount of heat required to undergo fusion. Knowing that these two lines, that this line is longer than this line, means that the heat of vaporization is greater than the heat of fusion. You need more heat to vaporize something than you need to melt something or to fuse something. And that's shown by the fact that this is longer than this. Very important you understand that. The last kind of math problem they could ask is heat calculations dealing with specific heat. Now, specific heat is the amount of heat required to change 1 gram of substance 1 degree Celsius, to raise 1 gram 1 degree Celsius. What does that mean? Well, it means you're adding heat to try to raise the temperature. Well, where is temperature raising? Well, temperature is actually raising at 3 spots on this graph, on this chart. At AB, temperature is going up. At CD, temperature is going up. And EF, temperature is going up. But what you need to concern yourself with on this regions is just CD. CD is the only part of the regions that they're going to talk about. They're going to be talking about heating something above the freezing or melting point and below the boiling point or vaporization point. So CD. Now, what's the formula that deals with specific heat? Well, you go to table T. Q equals mc delta T. Q equals the mass times C is the specific heat capacity of water, which we just went over what it is, the amount of heat required to raise the temperature. Mass times the specific heat times the change in temperature. There's a change in temperature here. There's no change in temperature here, and there's no change in temperature here. So you know if it's a change in temperature, you're dealing with this, and you're dealing with the Q equals mc delta T formula. So let's say they said, how much heat energy in joules is absorbed by 25 grams of water when the temperature of the water increases from 45 degrees Celsius to 55 degrees Celsius. So you see the question on the slide screen. You see the question. You know you're dealing with 25 grams, and you're dealing with a temperature change from 45 to 55. Again, the fact that there's a temperature change means you're dealing with the delta T formula, because that's temperature change. And the only formula that has that, Q equals mc delta T. Well, what's C? What's the specific heat of water? I don't know. You don't have to know. Again, table B. It's so easy. You go to table B, you see table B. 4.18 is the specific heat capacity of water. You go back to your problem and you just plug in the numbers. Q equals mass. Well, what's the mass? 25 times specific heat, which is 4.18. So 25 times 4.18 times the change in temperature. It goes from 45 to 55. It changed 10 degrees, because 55 minus 45 is 10. 25 times 4.18 times 10 equals, and you plug it into your calculator, you get 1,045 joules. That's the amount of heat in this equation absorbed by 25 grams of water to raise the temperature 45 degrees to 55 degrees. Remember, as long as they give you a temperature change, you know you're dealing with line segment CD. And it's very important that you know all of that. And one last thing about the different segments is that in line segment BC, which is fusion, which you know is going from solid to liquid or liquid to solid, that represents a phase equilibrium. Now, if you don't know what equilibrium is, you can go to the concept on equilibrium. But here, since this is solid and liquid, this is the solid-liquid phase equilibrium. And what temperature is that happening at? It's happening at the melting point or the freezing point, which in this case for water, if you could see that, is 0 degrees. So the solid-liquid phase equilibrium is at 0, and, you guessed it, back up to DE, the liquid-gas phase equilibrium. The liquid-gas phase equilibrium is happening at 100 degrees Celsius. All part of this table. Make sure you understand how to do all the math problems related to the heat calculations and the heating curve.